So in this video, I want to talk a little bit more about the octet rules and the just the formal charge calculation for this example. First, octet rule, and I covered a lot of this in the last video, but just to be clear, because there's some particular language here that I want to share with you. If an element follows the octet rules as laid out here, basically not exceeding 8, then you say that it's followed the octet rule. If it's sometimes I use the term expanded these octets like sulfur and phosphorus. You may also hear language like violate the octet rule. It means basically the same thing. All right, get that out of the way. Now, in this example, I've already, right, let's just rehash real quick. When I talk about calculating the octet rule and, what electrons am I counting? I'm counting the electrons that are either, dedicated to the element or to the atom with respect to lone pair electrons, or shared electrons. Okay, so like in this example, so we have one covalent bond equals 2 electrons. So we say this has the language would be has an octet of 2. It does not violate the octet rule. It's fine. That's what hydrogen basically always has for us. And the same thing on this side. This oxygen here, if I count them up, and usually I count them up by 2s, 2, 4, 6, 8. 8 electrons. Its octet is fine, right? Oxygen wants 8 electrons around itself. And notice that then if I talk about the octet for carbon here, those electrons that it's sharing between itself and hydrogen and itself and oxygen are counted for both elements. So the octet here, the box in red, right? 2, 4, 6, 8. So shared electrons are counted on both elements when you're doing the octet rule. Okay. Formal charge calculation. Now there are better examples for this, and we'll apply it over and over again. But there's 2 things to keep in mind for the formal charge calculation. One, you can do a formal charge for every atom. Like for example, this is the equation here, okay? And the formal charge is really like the exact charge on that atom, all right? Now, in this example, if I just pick on the oxygen as my first one, the formula says I take the number of valence electrons, I subtract the number of lines or bonds, okay? And then I subtract the number of lone electrons. Not lone electron pairs, but actual lone electrons, or that's why I use the word dots there, okay? So the valence electrons for oxygen and any member of that family, right? The valence electron count is going to be 6, minus the number of bonds. So there's 2 bonds, double bond, and then minus 1, 2, 3, 4 lone electrons. And what we see here is that the formal charge on this oxygen is 0. Now, if something is 0, we don't add it to the structure. So actually, the way I wrote this earlier was fine. I didn't need to add any zeros around the thing. Again, I'm just using this example to illustrate the formal charge calculation here. This hydrogen is the same as that hydrogen. Has a valence electron count of 1. All hydrogens have a valence electron count of 1. Minus the 1 bond that I see. There's no lone electron pairs. That equals 0. Great. The carbon here, formal charge, again, valence electron counts 4, has 4 bonds around it, and then it has 0 dots, 0 lone electron pairs. It's equal to 0. Okay, great. So illustrated how we use the formula. And then the second thing to keep in mind with formal charge is right here. The overall charge of the molecule needs to equal the sum of the formal charges. So what I mean by that, the overall charge of this molecule was 0, right? No charge is shown, so it's 0. And if I add in the formal charge, 0 plus 0 plus 0 equals 0. Okay, so again, this is, a simple example. All the formal charge is 0, add them up is a 0 for the overall molecule. That's what you want. In the next example, the next video, we're going to we're going to practice with this anion here. And in this one, what we have to do is that, when we add up the formal charges, then the total formal charge needs to equal to that -1 that's in this molecule. But again, we'll deal with that in the next video.